All right, so we're going to move on to the last talk. This is going to be Carl Hacker telling us about something I referenced earlier. Actually, this is some of the coolest work I've seen in a while, so you should enjoy it.
Hi, I'm Carl Hacker, and I'll be talking about subdividing the brain using specifically resting state data, and talk a little bit about supervised learning. So today I want to cover four main objectives. First, just introduce the fundamental techniques we use to analyze resting state bold data, and then talk about how we build parcellation schemes using these techniques, so more sophisticated derivative techniques. And then describe some of the structure we've seen from using these techniques and the special challenges that we face due to the hierarchical organization of the data. And then finally, how we can set up supervised learning problems to build on these techniques and address the challenges that we find due to the organization of the data. So I see the two fundamental techniques underlying most of the parcellation schemes as being either derived from seed-based correlation mapping or independent component analysis, which fall on two very different ends of a spectrum. So in seed-based correlation mapping, you're looking at the correlation between one region of the brain and every other voxel or vertice or however you've set up your data space. So this originally started with, of course, Biswall's 1995 paper, where they looked at task activation topography for a very simple motor task, which is just repetitive hand grasping. And they took one of the activated regions, B, and averaged the time course of that region in resting state data, and then correlated it with the rest of the brain. And of course, they found that the topography of these correlations very closely matched the topography of the task activation. So this, I think, is one of the key motivations for why we study resting state data, and that's that regions that respond to similar tasks have spontaneously correlated signals. So of course, there's many networks throughout the brain, and you can visualize these networks by putting seeds in different locations. So the seed in the posterior cingulate cortex in PCC is correlated with the regions in red, whereas the seed in the interparietal sulcus is correlated with the regions in blue. So the key idea between separating networks is that regions within the same network should be more correlated to each other than they are to regions in other networks. Depending on how you process your data, this may lead to the observation of anti-correlations between networks or simply a variability in the amount of correlation. So the key point is not whether it's positive or negative, but the point is the variability in the correlations that you see, that regions should be more correlated with other regions within the network and less correlated with regions in other networks. So this is on a very different end of the spectrum from independent component analysis, which seeks to basically decompose the data in a single step. So this is based on the assumption that we can describe all of the resting state data, the voxel-wise time series, with a small set of fixed spatial components that each evolve over some time course. So this means that if you took all the components shown below and had a time series over which they evolve, and you summed up the voxel-wise time series from each one of these components evolving over its time series, you would represent a large amount of the variance in the original data set. So this gets us closer to subdividing the brain into parcels, but it's not all the way there yet because these components can be spatially overlapping, and a given region can belong to multiple networks. So briefly to compare these methods, ICA is based around maximizing the independence of components that represent large amounts of variance in the data. On the other hand, seed-based correlation mapping is just the correlation of one seed with the rest of the brain. So it's essentially just looking at a single row of a voxel-wise correlation matrix, or whatever space your data is in. So spatial ICA is data-driven in that it's basically completely unsupervised, aside from the metaparameters that you use to specify what kind of algorithm you're using and how many components you ask for. Seed-based correlation mapping, on the other hand, is very heavily biased by the location of your seed region, And for that reason, it can be used to interrogate specific regions and specific functional systems. It's worth noting that a key practical difference between these methods is how you approach noise or spurious correlations in the data. So with ICA, this problem is kind of inherently solved by the method itself, where often noise components are found by the ICA algorithm itself. And so in the course of doing your analysis, you separate noise from data. However, with seed-based correlation mapping, the results are extremely sensitive to spurious correlations in the data, and they have to be explicitly regressed out prior to computing correlations. So I'm going to address some of the methods that are derived from these techniques and kind of the overall sense of how the data are organized, which is hierarchically. So when we say unsupervised learning in resting state fMRI, we mean that we're trying to organize the data into regions with similar statistics. So to find homogeneous regions. This could either be similar time courses or more often similar topography of correlation maps. So in other words, we're trying to find structure in unlabeled data. So like I said, seed-based mapping is heavily biased by the choice of seed region. However, we can approach an unsupervised method by systematically seeding the entire brain. This gives us independence from any prior information about where we should put our seed region. So how you divide up the brain for systematic seeding is important. In this example, it's simply a regularly spaced grid over the cortical surface, but you could imagine every voxel being used or some other parcellation scheme used as a prior to break up the brain into seeds. So if we look at the correlation maps that result from these different seeds, we find that widely separated regions can have very similar correlation patterns. So region A on the left is over the frontal eye field, part of the dorsal attention network. And you can see that it's correlated with region of the IPS and region MT. And when we put a seed in MT, we find a very similar correlation pattern. On the other hand, seeds in what we call the default mode network, for example, the angular gyrus in B, produce a very different correlation pattern than the dorsal attention network, but also produce similar correlation patterns to other seeds within that system. So the first strategy derived from this is based on the notion that nearby seeds may have very different correlation maps. And as we've seen in a lot of the other talks today, some of the idea of breaking the brain into components is based on the gradations in the connectivity profiles. So one method based on this idea is correlation gradient-based parcellation. So we're looking for boundaries of maximum correlation map dissimilarity. So for example, a seed in the supramarginal gyrus may have a connectivity profile that's largely insular or middle frontal gyrus, whereas a seed region in the angular gyrus has correlations with the middle temporal gyrus or superior frontal gyrus or the PCC. And if we kind of march along the cortical surface, putting seeds all the way along, there is some point at which we get a rapid change in the correlation topography. So in this example, it's right at R4 or 5, where the topography or the profile of connectivity suddenly flips from one pattern to another. So by performing this operation throughout the brain, we can come up with a map of functional connectivity gradients. So some further processing is required, including edge detection algorithms and some amount of thresholding to actually define where these important boundaries are. But after doing that, we essentially have parcels that implicitly are internally homogeneous because we've defined the boundaries where the differences are. Inside of that is implicitly regions that are similar. Another result of this method is that these parcels cannot be connected to distant regions in the brain. So it's inherently divided rather into networks. It's instead divided into parcels, which probably emphasizes an area level of organization rather than large-scale systems. But other methods can be used to further categorize them into networks, which we'll go over. Okay, so rather than looking for differences between seeds, we can also just simply ask where are similar patterns of connectivity. So just previously, k-means was brought up as a clustering algorithm, but we can cluster similar correlation maps in the data set using a variety of clustering approaches. So in this example, fuzzy c-means was used, which is very similar to k-means, although it allows a scalar membership to each cluster center. So the distance in this arbitrary space, or in this abstract space, from one correlation map to the cluster center defines how much it's a member of that cluster, but it can be, in some sense, a member of multiple clusters. So on the left is the solution for 7 clusters, showing a variety of networks like the default mode network in A, or the dorsal attention network in green. But the important point to draw from this is there are multiple answers that we can use. There are multiple numbers of clusters. So there's multiple good answers that we can get. And for example, we see this as local minima in a cluster dispersion metric, or the amount of error we get at each number of clusters. So I'd like to point out that we see local minima at, for example, 7 and 17 clusters, meaning that these are 2 reasonable solutions to break up the data. So using a completely different clustering algorithm and looking at seeds only on the surface of the brain, the previous example was voxel-wise. This is seed-based throughout the surface, and we find again that there are local minima in the instability of clustering at 7 and 17 clusters. So this says that these numbers are important in terms of what are the fundamental number of components in the brain, at least at this resolution of data and with this methodology. The second point to draw from this is that a cluster from a low-dimensional parcellation typically breaks into smaller clusters at higher levels. So the boundaries at the low-dimensional solution match up to the boundaries at the high-dimensional solution. So that means that these subregions or subnetworks are nested within larger systems, indicating a hierarchical organization of the data. So the fact that it's hierarchical and that we find the same number of components to be good solutions across data sets means that there's a reproducible hierarchical organization. So we also see this with graph theoretic approaches. So to form a graph out of the data, we essentially look at the correlation matrix and apply some threshold and binarize the matrix into a graph. So if you use a very low threshold, then you'll have lots of connections. So you'll have a very high tie density. And at a very high tie density, you find very large regions because the modules that a modularity detection algorithm would find would be large clusters. As you increase this threshold, you'll get lower tie density and break the data up into smaller modules or smaller clusters. But again, as we do this increase in threshold, we find that these large regions break up into smaller nested regions. So for example, this large cyan cluster here breaks up into 2 or 3 motor or sensory motor regions, 1 ventral, 1 dorsal. So a similar principle and structure has been found using independent component analysis. In this example, the authors did a very high dimensional ICA across a large number of subjects, and then used an agglomerative clustering method to build modules and then build systems out of these small components. So we see some of the very same topographies or same networks through the seed-based clustering approaches. For example, region M2 is a large sensory motor region. Visual, M1A is default mode network. And these are further agglomerated into 2 major systems called the intrinsic system and extrinsic system. So one of the major problems, as previously mentioned, is choosing the correct dimensionality in your data, or what level of granularity do you want to use for your particular research objective. So there is no general solution, and this does depend on the problem you're looking at. So if you were to use this parcellation, if your ultimate goal was to find group differences from a disease group and a control group, a very fine parcellation would give you sensitivity to differences in very small regions. So there's a trade-off of sensitivity to very focal effects from a fine parcellation versus having the statistical problems of many comparisons. So how we implement the decision of choosing a dimensionality differs across these, manifests differently depending on the method we're using. If we're looking at correlation gradients, then using a low gradient threshold, meaning getting lots of boundaries, would give you a high dimensional solution, many parcels. It's much more intuitive with the clustering algorithm. You just ask for more clusters. Same with ICA. You can simply specify increased number of components. And in graph modularity, this comes out as asking for a lower tie density, using a higher correlation threshold when building your graph. So this brings us to the key limitation of unsupervised approaches, which is not knowing exactly what the correct dimensionality is. But the problem is even worse than this because different methods may recover the same RSN, but it may come out at different hierarchical levels. So we may find a large motor system in one data set, whereas in another data set, the same method broke it up into smaller pieces. So when we desire a particular RSN entity, we may find that we instead found a superclass, meaning that RSN agglomerated with other similar systems, or a subclass, meaning we only got fragments of this RSN. So we may have unstable results across data sets. A consequence of this is that there's no guaranteed one-to-one correspondence between the solutions in multiple data sets. So we have two choices, as I see it, on how to handle this problem. We can either try to solve an assignment problem, which is matching up components across individuals or across data sets before doing our analysis, a problem that may have no solution if, for example, your ICA did not find all the same components in two individuals or in two groups. Or we can use a single group-defined parcellation and apply it to everyone. This, of course, ignores individual differences in RSN topography. So luckily, all these variety of approaches have produced very similar answers, and I'm kind of showing results at a 7-network level of parcellation. So we find very similar patterns corresponding to the dorsal attention network across methods. It's a subcluster in cyan in this particular parcellation. For example, the hand motor region comes out in Smith, and that's the orange region in Power. But in Lee, we get a very large motor cluster. So this brings us to how we can use supervised learning to address the challenges in this data. So briefly, to kind of explain the difference between supervised and unsupervised approaches, I'm going to use an example of handwriting recognition from sorting postal mail. So unsupervised learning is simply taking, for example, a whole bunch of handwritten digits and clustering the data, which would give you an answer like, these are the characters of the decimal system. These are the major clusters of the data. So this is a discovery approach. Supervised learning is an approach of classification, or to say, this particular number represents the number 2, or this particular image represents the number 2. So we came to the problem with predefined classes, kind of knowing what we're looking for, and we're just looking to assign any given piece of data to a given class. So with unsupervised learning, we can discover new structure in the data, and we're not really biased by a prior solution. But with supervised learning, we can avoid the assignment problem, meaning that when we try to find the default mode network in different data sets, we're guaranteed that that entity represents the same thing. We can also explicitly target variance in the data that's related to the components of interest. Essentially, we're boosting the SNR of the data by building a model beforehand for what we're looking for. So these are complementary, not competing approaches. Unsupervised methods discover meaningful components in the data. Supervised methods can then be used to optimally extract these known components from new data sets. And you're guaranteed a one-to-one correspondence in your recovered components if you use supervised learning. So dual regression is not generally considered supervised learning, but I'm putting it into this category because it's a method, it's the most common method used to extend group-level results to individual subjects. So typically, you compute group-level spatial ICA components, and then find the associated time courses for these components by regressing them into an individual data set, and then take that time course and correlate it with every voxel to recover the topography of that component in an individual subject. This allows us to take group-defined components and allow for variability in their topography across individuals. But I'd like to set up a more general problem of supervised learning in a more machine learning context. So basically, we're looking to find a mapping between an input space and a known set of categories. So in this example, we have an array of pixels that's the data for the handwritten digit. And we have a set number of classes, and which can take binary values where the desired value is that the classifier should say that this image represents the number 2 and does not represent any other numeral. And what we're trying to do is learn a function that maps the space of pixel values onto classes. So in neuroimaging, we may have an array of voxels, and we're looking to find some function that maps this to telling us that this is part of the motor network and not part of any other network. So to do this, we have to build a large library of training data. So you can't do this without kind of already knowing the answer based on some supervised solution. But we will take that from a group-defined parcellation, and we can then produce a variety of seed-based correlation maps across different RSNs and across different subjects. So we'll have a set of seed-based correlation maps, each one assigned to an RSN based on our group-defined parcellation. So if we learn an underlying function that maps correlation map topography to RSN identity, we can then go systematically throughout the entire brain, make a correlation map for every voxel, apply the learned function to these maps, and then get a map of RSN identity. So for example, on the left we have a variety of seed locations, their corresponding correlation maps. In this example, we used a multi-layer perceptron to learn this mapping. And for every point in the brain, we then get point estimates of the pseudo-probability of membership in a particular RSN. So I want to mention at this point that you can train really any components you want, and you can try to train RSNs at different hierarchical levels simultaneously. So many unsupervised approaches do not return a language network, but returning a default mode network or motor network is very common. But we can guarantee that we at least attempt to find a language network in any individual data set by learning the underlying mapping from all the variability of correlation maps at the group level, and then applying this to an individual. So how do we evaluate whether or not this is actually working? Did we just learn a mapping and it's returning us the same group level answer in every subject? Or is the variability that we're finding across individuals actually meaningful? So we can ask, in this example, we applied the classifier to voxelized data, which allows us to look at the variability of the functional representation or the functional topography in relation to the anatomical variability. So we asked, does function vary appropriately with structure across subjects? And we found that the topography of the motor RSN estimates conform to the gyral morphology of individual subjects. So this means that it's really fitting this RSN to the spatial organization of each individual subject's brain. To quantify this, we also looked at where the centroid of the motor system was with respect to the central sulcus and found a correlation in their Y position. Another thing we can ask, though, is what if we don't train every region of a network? So in this example, we need a large library of correlation maps that represent the variability of the motor network across subjects. That variability is learned by this underlying function of a multi-layer perceptron or any other supervised learning technique. So if we find variability across subjects, that means we've really learned some underlying function. We haven't just fit the noise in the training data. So another way to look at that is, can we fit regions that weren't in the training data to the correct RSN, even though they weren't trained? So in this example, no seeds in the thalamus or cerebellum were used in the training data, but we still produce a reasonable parcellation of thalamic regions and cerebellar regions that match up with unsupervised group estimates, even though no seed examples from that region were included in the training data. So why does this work? It means that we learned an underlying mapping for the correlation maps that these thalamic regions produce, and this underlying mapping was able to associate this with the correct RSN on the basis of the correlation map rather than where the voxel location is. So I want to compare linear methods to nonlinear classification methods. I'm just going to compare dual regression to the neural network method we used. So on the left is the result of regressing group-defined components onto individuals. And you can see that there's some amount of collinearity between, for example, the visual network and the motor network, or between motor and dorsal attention. So if we look at all the seeds we used to train this data, or just any library of seeds, and ask, how does the degree to which any location in the brain is part of the motor network co-vary with the degree to which it's part of the visual network, we find that there's some linearity. And this makes sense because in this data, these two networks are correlated. So this is the correct answer. These are linearly correlated networks, but our method produced a correlated answer, which means that it is not going to give us great specificity, although that is a true structure in the data. But using a nonlinear method, we can explicitly orthogonalize the probabilities, which increases the specificity of the topographies we find. So this means using these complex nonlinear decision boundaries, we've been able to make the degree to which something is an element of the motor network independent of the degree to which it's part of the visual network. And this results in greater spatial specificity. So this is not really part of the data. It's kind of an artificial thing we've introduced, but we do it to enhance the spatial specificity for the purposes of parcellation. Okay, so finally, there are some interesting tricks that we can perform after we have a supervised learning algorithm. So we can use it to optimize our methodology. So because we kind of came into this problem knowing the data and knowing the correct answer, we can ask how well can a supervised algorithm learn this mapping as a function of any parameter in our methodology. So we can ask how well can a classifier perform as a function of how much data we use. And we see, of course, as we include more data per subject, we can get less error in this mapping. And so there's kind of an elbow right around 10 minutes, meaning that if we used 5 minutes of data, we can't expect to get very good estimates in individual subjects. We also looked at ROI size and found a surprisingly large seed ROI radius being optimal, 10 millimeters, which was much larger than we used, but this probably represents the resolution of the data, the blurring across subjects, and just the peculiarities of the data we used. Okay, so when you're setting up a supervised learning problem, there are several key design considerations. You need to build the variance of whatever you're looking for into the training data. So if you must give examples of whatever RSN topography you're looking for in the training data set. And you must encode the variability across subjects. If you only include examples from one subject, a classifier is only going to learn that topography. So hopefully, if you include enough subjects, a classifier can learn variability across subjects that can then generalize to new untrained subjects. So of course, the subjects you use to train the model, you want to be similar to those in your test data set and be acquired with similar parameters and have similar preprocessing. So if we do global signal regression in one data set and then try to classify a data set without, it may not work so well. So we'd want to keep the preprocessing consistent across groups. So key points from this are that a variety of unsupervised approaches have been successful in producing sets of canonical RSNs, and they're remarkably consistent across methods despite using very different methodology, whether it's seed-based or ICA. Because of the hierarchical organization of the data, finding solutions that are comparable, a one-to-one match between different data sets, can be difficult if these methods are used independently on different data sets. However, by using supervised learning, we can guarantee a one-to-one mapping, and we can guarantee that we recover reliably the same component in each subject. And that's all I have. Any questions?
So I can start off with a question while others are thinking. So Carl, maybe you can tell us about how this might be particularly useful now that you've been able to train for these networks. How might you use this in other groups of subjects, say clinical populations, that sort of thing?
So we've applied this to a couple different clinical populations. I think the one that's most notable is in tumor subjects. Various brain tumors can cause mass effects where functional regions are shifted from one place to another. And so this is a good test of the generalizability of this method. So you can imagine if you have a tumor in the sylvian fissure and it shoves Broca's area forward, presumably that region might still have similar connectivity despite being in a different location. And we found that this method can correctly identify the new location of Broca's area on the basis of its connectivity in an individual subject, even though it's at a new location. So that's one example of how we've used it. Yeah.
And I was wondering, how about stroke recovery? Did you see some?
Yeah, so it depends on the size of the lesion. So you can imagine if you do enough damage to the organization of the brain that it no longer resembles the training data, then you can no longer reliably recover networks. So this approach is best for small perturbations in the anatomy or function of a subject that are still reasonably close to what the networks look like in normals. If your data are so different from normal that, well, at some point you need to use an unsupervised approach to learn new networks in the distorted individual.
I would like to thank you for your very interesting talk. And I also think that you are the right person to answer a question that is puzzling me already for some time. And that is, on the one hand, you have this independent component analysis, which is based on statistical ideas on that some items are statistically independent. On the other hand, you have clustering methods, but so they are completely opposite in the basis of their assumptions. But nevertheless, if you look at when you apply them to fMRI data, you get very similar networks. Now, the question that is keeping me busy already for some time is that is there a mathematical reason for that these completely different methods give the same answer? Or is it due to the data that we are analyzing that we get similar results?
Well, I'd say both. There is a mathematical reason, and hopefully it represents something in the underlying data. But I think the intuition is that both of these methods are looking for regions of similar signal, of homogeneity. So the weights in an independent component that are returned represent regions that have similar time courses. And that's kind of how the clustering works as well. It's a different mathematical method to get there.
But now for the independent component analysis, we assume that we have spatially independent components, but we don't see anything about the temporal behavior. So how does it come then that we get that we get these?
Well, it's my understanding that for a given component, the regions with very high weights for that component have similar time courses.
Yeah, that is the result, but that's not the assumption. So,
I guess the mathematics of ICA are perhaps outside of my expertise.
Sorry, yeah. Then we'll talk later. Yes, thank you.
Hi, yeah, I agree, this is neat stuff. Just a couple of sort of detailed questions, if I could. One is, so I think you showed an example where you had 8 ICA components going into your unsupervised part of the...
8.
I'm just wondering how robust this is to the choice of the number of
So like
ICA
how many
components.
RSNs you use? Yeah, so we find 7 is a very easy problem. We expected, like, okay, we're going to try to train a neural network. It's supposedly very difficult to do this. It worked like the first set of parameters we tried. So actually, LDA can do this very well. Dual regression works, which is just linear regression. So with this number of components, it's actually a very easy problem. When we talk about trying to build a classifier for every individual area, if you're here for Matt's talk, the approach he's using is to build a classifier for every individual parcel and say, just make it into a binary classification problem of inside versus outside.
Right. And it looks like you did PCA to reduce, so you're not
Yeah, so-
entering every voxel as your inputs to this network?
Yeah, we start out with a PCA on the correlation maps just as a dimensionality reduction. This is, of course, the first step in ICA as well. Partly this is, we can represent, 99% of the variance with far fewer data points.
Yeah.
And it just makes the training of the neural network 1,000-fold faster.
And last one, if I can. How many, just a detailed question, maybe it's in the paper, but how many units were in your hidden layer?
Yeah, so I think, so we ended up with actually a lot of input components. We tried, 10, 100,000 PCs. We ended up using about 1,000 PCs with 22 hidden layer nodes.
Oh.
So it's actually a small dimensionality in this hidden space that was optimal for finding 7 networks. But presumably, if you're looking for more networks, this is, with this resolution of data, if we try this on the HCP data set, I'm sure we could get more performance with a higher number of nodes because there's more detail in the data.
Nice, thank you.
Thanks for the great talk, Carl. So just one question I have. Sorry, it's kind of broad, but so what do you think is the best way to learn representations from fMRI data that are not only useful from like a data science perspective, but also neurobiologically valid? So how would you answer this question in the context of the methods that you have been using?
So we can take the values at the hidden layer and do a reverse mapping and ask what is the spatial topography of what these hidden layers mean, or and probably nothing, or maybe, the point of this is that we don't need to know what the hidden layer means in order to have a meaningful representation. So what we're really looking at here is the ability to learn the mapping because it's an arbitrary function. In the same way, we don't really care if the PCs actually represent something biological. It's just a data transformation, a way to represent the data with less variance. So I think you're looking at a very different question, which is I want a transformation that at every step of the transformation has biologically meaningful representation. And I think by investigating the topography of what these hidden layer units mean, we may learn something about building blocks of RSNs, but that's not necessarily the case. And I think that if you enforce that every stage of my data transformation must be biologically meaningful, you're limiting the numerical power of your approach, but it allows you to kind of maybe make a more organic understanding of how these features build together.
Okay, thanks.
So.
Thanks for the talk. I wonder, because I do notice this is kind of a relatively whole brain kind of a classification, and I wonder, or maybe you can comment on applying this method within a relatively small region, such as the hippocampus or thalamus. Like, have you tried that?
Yeah. So, okay. So, well, we have looked at what if you only classify using correlation maps in the contralateral hemisphere. So what if you restrict the region the classifier can look at to only contralateral connectivity? We found similar, slightly less performance, but you could do the same thing where you try to classify the entire brain based purely on its connectivity with the thalamus or with the cerebellum. So the performance will degrade, but I think it's an interesting approach to say how much information about connectivity is stored in the connections with a particular structure. So you could ask, how well can we separate cortical networks on the basis of their cerebellar connectivity, which has kind of been done by the Yeo and Buckner group to some degree, not through a supervised approach, but just by clustering the cortical connectivity of cerebellar seeds. The other way around. Okay, so maybe you meant to parcellate, for example, the hippocampus based on its connectivity with the full brain?
Yeah, like using this method just to parse it, like the hippocampus.
Yeah, so I mean, if you have enough resolution in your data and high enough quality data, then this approach could be applied as is to any voxel of the brain, meaning that any voxel in the hippocampus should have a correlation pattern with the rest of the brain, which if you learn a successful mapping, you would be able to map that to RSN identity. Yes?
I'd like to say I found all of the speakers this morning fascinating and extremely interesting, but from my perspective, in part a bit troubling. There was one technical question, and that is if you inject a dye into a cat's brain, into a specific area of a cat's brain, and then sacrifice the cat later, are you really mapping neural networks, or are you mapping venous or lymphatic networks? That's the first question. The second question is, I'm a clinician, and I came here because I'm really interested in finding how brain areas are injured and how that compares with the clinical effect on the patient. And you did answer in part several questions related to that, but there's one big question which I don't really understand, and that is if you have a viral infection of a patient's brain and the injury is caused by an off and on autoimmune reaction to specific areas of the brain rather than specific particular areas as has been mentioned today, and when that patient is fatigued, or whether it's chemically or physiologically fatigued, and that area of the brain increases and decreases as to the area of injury, how do you measure autoimmune injuries of the brain in relationship to what you're doing?
So I think
Maybe I'll do the first part, and Carl, you want to do the second part?
that would be great.
All right. So if I'm remembering the first part of the question here, it was, what is the relationship between injecting a tracer into an area and seeing the connectivity of that tracer versus what you're doing with a resting state approach, where you're looking at correlations in time series. Did I paraphrase well enough there? Yes, no? All right. So one of the really cool things about resting state functional connectivity, which I didn't have a chance to show in this talk, but I'll be showing later this afternoon, is that you can with just the bold fluctuations, the functional connectivity of the bold fluctuations, you can actually see very fine-grained connectivity patterns that are anatomically known. For example, between V1 and V2, we know from extensive studies in not in humans, but in monkeys or even in lower animals, that a given part of the visual field in V1, such as, let's say, 9 degrees eccentricity and 45 degrees polar angle, is going to be most connected, and this is what you would see if you do a tracer injection, to that same location in V2, that would be 9 degrees eccentricity and 45 degrees polar angle. And we can reproduce those connectivity patterns with functional connectivity. So we don't think it's just simply vasculature or lymphatics or something like that. The functional connectivity really can reproduce known anatomical connectivity. And Carl, you'll take the next part.
Yeah, so regarding the clinical correlates in resting state data, I'd say, first of all, it's remarkable that spontaneous brain activity can recapitulate the topographies of behavior. I mean, I think that's something we need to, consider, is that this is just spontaneous activity. This isn't even a task response. But we still don't know exactly what the function or purpose of spontaneous activity is, why all these circuits are communicating at rest. And further, I think the impact on resting state networks of various disease entities is even less understood. There are certain processes that we have found some correspondence with. For example, the default mode network topography somewhat matches the deposition of plaques in Alzheimer's. But, you know, we don't really know what happens to, you know, the one-to-one mapping of function of a region to a behavior to its spontaneous activity. So the kinds of studies that we would need are something where we have a set of very well-defined lesions in particular functional areas, observe the functional connectivity changes, and relate those to behavior. And that's still a subject of active investigation. So when you talk about, you know, a distribution of an autoimmune effect, I think that's way beyond where we are right now in terms of, you know, just nailing down what does this one topography mean, how does it change in disease, do changes in this topography, are they reflected in behavior, and so on. So I think the first, you know, a simpler approach would be to start with lesions from surgical procedures or strokes where you have a much better defined region rather than temporally fluctuating lesions from autoimmune diseases.
All right, thank you very much. The session is now finished. If you want to know more about the parcellation, you can come to see us and ask us questions personally. We're always happy to discuss with you guys. If you want to know more about what's going to happen in the next year, well, thank you in advance for giving a good evaluation to the session. So you probably receive like a questionnaire by email. And so if you give the highest note, it's probably going to happen again next year. We'll do another session like that with the most recent development. Thank you all for coming, and we hope to see you next year.
Also, thank all the speakers who came to talk.
Oh, yeah. Is that the part where like, I'm guiding you all for a bit?
So, are you wanting to know how you can do it yourself, or are you wanting to know the algorithm?
Well, you said that there was probably available.